Hello, welcome back to the last session of our discussion on the final exam solutions for the DSCA course. We are going to discuss from the question number 16. Now, look at the question here and the circuit. We see that D flip flop is given, and then there is a clock with a not signal. That means it's a negative edge triggered clock. Both the flip flops of the same type, and there is a connection between Q bar to D. Now, we have seen a latch sometime back, RS latch, S plus R prime, S prime latch, which is part of the circuit where D flip flop is also built up with. If you know, the purpose of D flip flop is to latch whatever value that comes in as data, which is input D, into Q. Okay, the whatever is a D will be the Q value when there is a clock edge here, and if there is a not when the clock edge is negative edge trigger. That means when it moves from high to low, whatever is the value at D will be latched inside. So it's a flip-flop which is actually operating on a clock edge. It could be a positive edge if they throw the not, otherwise a negative edge. Now let us understand the question first, and then we will understand what happens exactly to answer this question. Now draw the waveforms of Q0 and Q1. Okay, this is Q0 and Q1 depicting its changes with respect to the input clock. Assume that initially both the flip-flops are clear to 0. So we need to have a state, because the D flip-flop always stores one value, one bit value, either a D 0 or 1. So we can assume anything. Now it is assumed that we have cleared the flip-flop. That means Q is 0 and Q bar is 1. Remember, always this is a complement. Q bar is a complement of Q. So Q happens to be, when we say it's clear to 0, we are saying Q is clear to 0. That means the value on at Q, what you see on each flip-flop is 0. That means Q bar is expected to be a 1, which is fed back to the individual inputs of the flip-flop. But when does this change happen? See, the D value can be anything, but it will not go into the flip-flop unless this particular condition is satisfied. That means clock edge is moving from high to low. It's a negative edge triggered flip-flop. So it actually stores the value in D only when there is a transition happening at that particular edge. It's a edge triggered, and that's why it's called flip-flop. If it is level and if it doesn't have a clock, then it's a latch. Now you need to show only Q0 and Q1 for 4 clock cycles, but I will draw it for maybe we can draw it for 4 clock cycles and align the outputs with the clock edges. Okay, we need to make sure that when we align the transitions, it should be aligned with the clock edges, because all the transitions and changes happen only during the clock edge. And remember one more thing, here Q bar of the first flip flop is going into the second flip flop, F of 1, flip flop 1. So any transition happening with in Q bar of the first flip flop will be the clock for it. Okay, there is no separate clock. We are giving Q bar itself as a clock. So a circuit can be anything. Okay, so let us look at this question now. Okay, so the explanation has been given. Now we need to draw the waveform. So let me first try to draw the clock edges. Okay, 4 clocks are given, supposed to be given. So let us draw 4 clock pulses. This is one clock, up from this to one clock, and then this is another clock. Okay, these are all a complete clock cycle. Now which is a positive edge? This is positive edge trigger. That means it moves towards the positive value, which is this is 0 and this is 1. Positive edge trigger means the clock edge which moves towards the positive, and negative edge trigger means it is going down, from 1 to 0, negative edge trigger. So when you have a symbol like this, it's a positive edge trigger. That means the transitions do happen during this clock cycle edges. Whereas if I have a not here, the transitions happen, or the value in D will get latched here during the negative edge term. Okay. Now that means what? Both are negative edge trigger. That means the transitions can happen only during this time. So let me only draw the negative edges. We are no interested about only these edges. So let me draw this negative edges. Okay. Now let me call this as a Q naught and Q naught bar. Okay, Q naught and Q naught bar. Okay, because the flip flop is 0, f of 0. This is f of 1. Q naught is taken from Q. Now what is the initial value? They are clear to 0. That means Q naught is equal to 0 initially. Q1 is also initially 0. So let me, this is a clock CLK. Now let us write Q naught. So until the negative edge there is no change, and it is supposed to be 0 now. So let me write Q naught as 0 here. Okay, this is 0. Something like 1 will be here. Now since Q naught bar is going as a clock, let us draw Q naught also, though it is not asked for. Okay, now let me say this is 0 and this is 1. If initially Q naught is 0, Q naught bar will be a 1. So up to this. Why am I not drawing beyond it? Because I don't know what will happen based on the circuit. This edge will create some changes to it. So let us stop here. What is happening? Let us observe it. Now what about one more thing? Because we are supposed to write Q naught and Q0 output, right? So I need to worry about Q1 also. Okay, let us Q1 also. Let me draw the. Okay, so Q1 is also 0, right? So let me write it 0, 1. Q1 is also 0. Okay, this is supposed to be Q1. Let me draw it properly. Okay, now what happens? This transition happens. Okay, clock is going from high to low. This edge is going low. That means whatever is the value of D should get latched. Now what is the value of D? D is nothing but Q0 bar. Q0 bar is 1. So this value 1 is waiting at the input here. And then the clock edge is going down here. Then it is supposed to latch this 1 into this. The Q was earlier 0. Now it should become 1 because the input is becoming, its input is 1. So 1 gets latched. Now when Q0 becomes high, Q0 bar will naturally become low. Correct? Okay. Now this is what is happening. Now this is a positive edge. Will there be any change? No, because this is D flip flop is not going to respond to any positive edges. So let us continue crossing this edge. So far we can continue. Now what about this Q1? What has happened is Q0 bar was 1 and it went down. Correct? It's a negative edge. Q0 bar is the signal which is going in. As far as the f of 1 is concerned, clock is coming from this signal for the f of 1. And this has gone down. Correct? That means it is supposed to latch the value whatever is here. It should latch into this flip flop. Now what is the value? Because initially Q1 is 0. This will be Q1 bar, right? Q1 is 0, then Q1 bar is 1. That value is waiting outside and the signal is going down. That means it is supposed to latch that value, right? So when it latches, this is supposed to become high, right? Q1 is going to become high. Now let us look at this value. it is going down. Now, when this happens, what will be the value of Q naught? Q naught is going to latch the value which is there in D. Now, what is the value? That is Q naught bar. Now, Q naught bar is currently 0. So, 0 will be waiting at this during this time when the transition happens. Now, at this point, Q naught bar is 0 here, because this Q naught is 1, then this is 0. In here we have seen that this value of 0 is waiting here and the clock edge is going down. That means it should latch that 0 here. Then it continues to 0. Now, when Q naught becomes 0, you can just draw this Q naught bar without any problem, because it is going to be a complement of that. Now, what will happen to Q1? Just see that. Now, F1, which is the flip-flop having the value Q1, is triggered by the clock, which is changes happening to the Q bar, Q naught bar. Now, Q naught bar has gone up. That is not going to impact this flip-flop. If it was not a negative edge trigger, then it would have created a problem. But this is positive edge. So, Q1 is not going to be impacted by a positive change. So, it will continue to be 1. Now, let us see. At this point, what happens? Again, a negative edge. Then Q naught bar is 1. So, that is what is going to be waiting here. So, when the clock edge goes down, it is going to latch that value 1. So, Q naught is going to become 1. Now, it will continue because this change is not going to be impacting anything. So, it is going to maintain this. But when this goes up, this is going to go down. Now, this change is going to be impacting, this is impacting, and this is going to impact this guy. Okay. So, what happens? When this goes down, what is the value being fed? Q1 being 1, then Q bar 1 will be 0. So, 0 is waiting at the input now. Okay. Compared to the earlier one. Now, this clock, which is Q naught bar, is a clock for this. As far as this is concerned, it is going low. So, it is going to latch the value which is waiting at the input, which is 0. So, it is going to become a 0. So, it will continue up to this point. Now, what happens here? This is again a negative edge. Q naught is going to react to that, and Q naught bar is 0. So, 0 is going to be waiting here. That means it is going to latch a 0 value. So, this will be like this. If it becomes a 0, this will become 1, and this is the output. Now, later on change will happen, but we are expected to only draw the waveform for the first 4 clocks we have drawn this. So, this is the waveform which you are supposed to draw. So, this circuit need not be the same. What you get may be something else. In that case, you should be able to make out whether it is a negative edge triggered or a positive edge triggered, and the connection is where is the signal coming into D, what is the value of D at the time when the clock edge is changing, that should go into the flip-flop. Then Q will become that value, then Q bar will naturally become the complement of that. So, that's what is the way you should operate this and try to get the output. I think if you understand this and follow clearly, any circuit given using the flip-flop with clock edges, you should be able to, and initial values. Please remember what is the initial value also should be understood, and accordingly you should start with those values here and then continue. So, I suggest that you change the circuit assuming that initial value is 1, or assume that this value is, instead of negative edge triggered, is a positive edge triggered, and then that means the knot is not there. Then what happens? If you do that, then you will be able to understand this particular problem. Okay. So, this brings to the end of this discussion on question 16. So, let us look at the question 17. This is a simple Boolean expression simplification. Okay. It's not simple. There are many steps are there. You are supposed to have knowledge on all the basic Boolean algebra laws that we have, the rules we have learned in the initial stages of Boolean algebra. So, let us look at this solution. I am not going to spend too much time here because it's direct applying the different distributive law and other laws. So, let me just go through the steps. Now, you have an expression given like this. You have to keep bringing in the values and then making it into a larger expression. So I am applying a distributive law. So a b bar comes into this a b bar c plus a b bar b d, and then a b bar. Now we are just doing multiplication of only this part of the expression. Then the remaining thing is left as it is. So we have to be very careful that we don't make any mistakes in the calculation. Now what happens? B bar. Now when you have, let me explain this. This symbol, okay, what is given is four inputs and an AND gate, right? This is the expression, right? A, B, B bar, and D. These are the inputs given to the AND gate. Now we want to see what is the output of this expression. Okay, this expression will be, if B is 0, this is going to be 1. If B is 1, this is going to be 0. That means one of the values is going to be 0 here. If at any point in time, one of the input is going to be 0. That means if AND gate anything is, one of the input is 0, output is going to be 0. So this expression can be totally considered to be 0. Okay, that's why this is done. So we are making it 0. We are removing that expression altogether because it's not going to add any, it's not going to contribute to the result of the previous other OR operations, because this is going to be 0. Then it's a non-trivial, and then we can remove it. Okay, now we have applied the drop the 0, then the remaining expressions are considered. Now apply distributive law again because you are bringing the C inside. So this is what is done. Now this, from here you go to the step 6, CC. Now what is CC? It doesn't matter whether you have C any number of time. Okay, if you are adding all of them, it's supposed to be only C, correct? Whatever is the value here, 1.1.1 is also 1. Okay, or 0.0.0 is also 0. So we can replace it with one value. So a b bar c, this is what you get. Now b bar c is common here, so we can take it out, and a plus a bar. Now what is a plus a bar? A plus is OR gate. Okay, this is a and this is a bar. Either this is 0 or then this is 1. If this is 1, this is 0. So one of the input is going to be 1, then this output is going to be 1. So this can be replaced with 1, that b bar c dot 1. Now when you have b dot c bar dot 1, you can ignore this because it's a AND gate. If you are having three inputs, one is always 1, then the output is going to be based on the only three other two values, because this is going to be, don't care, because it's not going to contribute to the value of output. So you can just say b bar c. So that's how you simplify it. And if you remember the laws, you can mention it. Rules, okay, rule number is not supposed to be mugged up and remembered, but at least apply this one by one logically and understand it by with the explanation that I have given. Any given expression, you should be able to simplify it and write it in the exam. Okay, this brings us to the end of this discussion on question 7. Now let us go into question 18, which is very, very interesting problem in this whole course, wherein we are trying to understand about signed and unsigned arithmetic. Now let me explain. You are given a 4-bit value. Okay, we are assuming a 4-bit ALU operating on 4-bit values like full adder that we saw in the previous discussion. Assuming that these two values are unsigned, perform the arithmetic. Unsigned, and then assume that they are signed. That means they are in 2's complement form, and perform the arithmetic. And then say, show what are the equivalent decimal numbers are getting added and whether the result computed in each case is correct or wrong. So let me explain this. This has been a tough thing for students to understand, and even the senior experienced engineers have difficulty in understanding this. Now let us look at 4-bit values. What all we can express it in using 4 bits, from 4 zeros to 4 ones, right? These are the 16 combinations that you can represent. Now these 16 values, you have a freedom to interpret them as signed number or unsigned number. Now what do I mean by that? See, if a given pattern is supposed to be an unsigned quantity, then you are going to assume the values are from 0 to 15. Okay, that means suppose I have 111, I will say this is 2 power 0, 2 power 1, 2 power 2, 2 power 3. Then I am going to add 8 plus 4 plus 2 plus 1 equal to 15. I am not going to treat this number as a signed number. Remember, I am not going to treat it as a signed number. If I don't treat this as a signed number, I don't think that it is represented in 2's complement. I don't assume that it's a 2's complement form, trying to find the amplitude of it. Okay, I will extract the amplitude directly from by substituting the values of the weights of each of the bit positions. But if I say that it's a signed number, then I look for a MSB being 1. I will say that either it's a 4-bit signed number or 8-bit signed number or 16-bit signed number. Based on that, you have to see that MSB of that particular bit is 1 or 0. If it is 1, it's signed number. If it is high, if it is 0, it's a negative number. Otherwise, it's a positive number. Provided I say that it's a signed representation. So the same value, suppose if I say that this 111 is supposed to be a signed number, I need to get minus 1. How do I get it? 1111. I told you earlier that if I assume it to be a signed number, it is already in 2's complement form because it is MSB is 1. Then if I want to know the magnitude, I should find the 2's complement. How do I find the 2's complement? I find the 1's complement plus add it. So all zeros, then add 1, then I get 0, 0, 0, 1. So the magnitude is 1. That's why it's minus 1. That's all. So this number will be treated as a negative number. And let me take, this is a very controversial number. So let me take this. Okay. This is 1, 0, 0, 0. I say that this is signed number because it is 1. Now I want to know the magnitude of this. So I will find 1's complement, which is 0, 1, 1, 1. Plus 1 I have to do because 2's complement I am calculating. So that will be 0, 1 carry here, 1 carry here. All carries go. So 0, 1, 1, 0, 0, 1. I get back the same number, but that doesn't mean it is a negative number here. For us, it's a quantity 8. So it is minus 8. That is the reason you see that the sign numbers is varying from 0 to 7, whereas negative numbers go one more, minus 1 to minus 8. Now, what is the advantage of this representation over sign magnitude representation? Now, sign magnitude representation means sign bit is separated and the magnitude is separated. Okay. In the same setup, if I say this is sign magnitude form, this 0, 0 is 0 is fine, but 1, 0, 0 is also 0 because this is minus 0. This is minus 0, this is positive 0. So for a 0 value, I will have two representations in the sign magnitude form, which is not used because that is also very complex to perform arithmetic in the digital circuits. 2's complement advantage is we can actually mix both unsigned and signed representation. By looking at the flags, we can decide whether we are performing a signed arithmetic or unsigned arithmetic and extract the value. Same hardware can perform both signed and unsigned arithmetic, and whether overflow is there or a carry flag is there, based on that we can assume whether the value what you have got is being represented within the limits or not. I will explain that to you. And then there is no wastage of values. Okay, we are not having two representation for 0. 0 is only 1, and there is no positive 0, negative 0, and we use minus 1 to minus 8 for the remaining combination. So every combination of values are used for representing the numbers, both in signed number as well as in unsigned numbers. So this gives an explanation about how signed and unsigned numbers are represented in 2's complement form. Now we are going to use this to perform this arithmetic. Now let us assume both the values are unsigned numbers. That means I am going to forget this representation for a while. Okay, I am going to forget about this representation. I am going to consider bit patterns here given here are representing these values. Okay, only these values. Now let us do unsigned arithmetic. Okay, now what is 0, 1, 1? Let me write the value. It is 7. Okay, this is the value, this is that 7. Now what is 1, 0, 0, 1? 1, 0, 0, 1 is here, it represents 9. So let me write it as 9. Now let me perform the arithmetic plus. Now arithmetic is done the same way. Okay, full adder whatever we have, we are going to do it. But you know that initially there is no carry value coming for the first bit position. So 1 and 1 is 0, a carry value 1 is going, so this will be 0, another carry goes 1, and that will be 0, another carry goes 1, 1 1 1 is again 0, then another carry goes, and then a carry out. Now, what is coming in inside the 4 bit is the result. Okay, this is supposed to be the result, which is, it says the result is 0 and there is a carry flag. Now, if I perform 7 plus 9, am I supposed to get 0 here? Certainly not. So, there is something wrong. Now, what has happened? It is supposed to be 16, correct? But it shows as 0. That means there is a overflow. Now, that means, let me not use the word overflow. It's not possible for us to represent the sum of these two numbers, which are unsigned numbers, into the 4 bit. How do you find out? Based on the carry flag. If I get a carry out of the addition, if it is set, that means this value is wrong. The result what I got is wrong. That's all you are supposed to write. I think this is very clear to you. Just treat them as a unsigned number and then try to find out the result. Now let us do it by considering them as a signed number. Okay, let me use a different color now. Now let me, given the same number 0 1 1 1, and then I have 1 0 0 1. Now I'm going to treat them as signed number. Okay, remember one thing, the hardware which is being used for adding this thing is same. Only thing is, we are now looking at the bit pattern into the bit pattern in a different way. We are going to assume that it's a signed arithmetic which is happening. In that case, now you may wonder how will the processor know? Processor doesn't know. But when you are declaring a variable in your C program, unsigned number or signed integer or unsigned integer, the processor or the compiler which is looking at the code generates the assembly instructions which will interpret different flags to find out whether the value is correct or wrong, the result is correct or wrong. So let me explain it. Now let us understand this 0111 correspond to what value in sign arithmetic. It is the same. 011 is same. Sorry, it is not 0110. It is this value. It is 7. So sign number is 7. Now what is 1001? 1001 corresponds to minus 7. So this corresponds to minus 7 in our signed number. If it is treated as a signed number, we will not look at this and then say it's a plus 9. We are going to treat it as a minus 7. Now if you perform the arithmetic, you are going to get the same thing. Okay, this is going to be 0, there is going to be carry, okay, and 0, there is going to be a carry. Same hardware is doing it, so there is nothing different. I'm just showing it for you once again, but actually the same hardware would have given the value like this. Carry flag would have been set. Okay, now what the result you have got, actually 000 is correct because 7 minus 7 is 0. So this value is correct. Now how do you know this value is correct? Because the processor doesn't know whether it is performing a arithmetic which is signed arithmetic or unsigned arithmetic. So whatever value it gets, it cannot deduce whether it is correct or wrong. Now what is being done is overflow flag is used for that purpose. So let me explain what I mean by that. Now there is a flag, so let me use a different color so that we understand clearly. Okay, now this value is 1. Okay, let me call it as carry carry A, and this is carry B. Now carry A, carry B are two values which are always, when you are 4-bit arithmetic you are doing, the last two carries are always taken in and fed to an XOR gate. Okay, XOR gate. And then what is coming out is called overflow flag. Okay, this is a flag. Now this happens to be 1 and this is also 1 and overflow flag is 0. So when I have a carry which is the same in both the cases, previous two carries, then I will get a 0 value as overflow flag. Now when there is a overflow flag, okay, which is 0, then the result that you have got is valid and correct for a signed arithmetic. If it happens to be 1, then the signed arithmetic is wrong. Okay, there is a possibility that both signed and unsigned arithmetic could be wrong. But you have to perform this arithmetic and then check whether the overflow flag is set or a carry flag is set. If carry flag is set, okay, it is equal to 1, then unsigned arithmetic is wrong. Means you cannot express it within the given number of bits. If overflow flag gets set, then signed arithmetic performed is wrong. You can also verify it with the decimal equivalent and make sure that what you finally say is correct or wrong. So you may be given any two numbers which are 4-bit numbers, of course. I am sure even if I give you 5-bit number, you should be able to do it, but at least to make sure that you don't find it very difficult, it is going to be given as 4-bit values. So you should be able to perform this. So what I suggest is take different combination of these values, okay, whatever bit patterns you have, any combination, perform the addition and then look at those values of unsigned and unsigned and see whether the overflow flag is set or carry flag is set, and the result what you are getting, is it matching with the actual normal decimal arithmetic you perform. Okay, either this value or this value you perform it, you will be able to understand it and appreciate this. Okay, this is very important concept which you are all supposed to know as a computer science engineers. Okay, then now we are now almost close to finishing all our discussion. Question 19. Okay, this is very important thing which was taught in the part of this course. See, as I told you, this is a digital system and computer architecture. So what is being taught about the computer architecture is the important thing is memory to CPU interaction. Now there is a address bus, there is a data bus. I show address bus as single direction because address is always given by the CPU to address a particular memory location, and the data is given either by the memory or it is written into the memory based on whether read cycle happens or a write cycle happens. If you are the CPU is performing a write cycle, data is fed into the memory. If it is reading from the memory, data is given out by the memory and the CPU is reading it. Now there is a handshake between them because you have to understand that the signals are going between the CPU and the memory, and CPU is the master and the memory is a slave. And moreover, you also aware that the CPU runs at a faster clock rate because of the technology difference. Memories are always slow. So there is a way a slower memory can interact with the CPU by saying that I am not ready with the data, so please wait. Or I am not able to write the data that you have given me into that particular location, so wait. So always the CPU is running faster and it is trying to wait for the memory to complete this job. So the handshake is designed such a way that the CPU and memory can be interfaced, whether the CPU and memory are of the same technology or whether they are running at the same clock rate, or CPU is very fast and memory is too slow. Still the handshake signals make sure that they work together without any problem. So that's what I'm going to explain by going through these signals. So you may be given different signals in the exam and you should be able to understand it and explain it. See, normally this will be given what actually means the values of the signals, because without that you will not be able to understand it. But what you need to understand is how the signal is flowing, whether there is a bar or a hyphen is there, which is a active low signal or active high signal. Now you see this here, clock is given as a positive edge, so any changes are happening during the positive edges, whereas memory request is a active low signal. Okay, and the read is also active low because read bar is there, write bar is there. That means what, when the value is 0, it means that write operation is done. Now the value is not given here, but there is no change here. That means it is not actually performing any read operation, and it is not, you cannot say CPU is here. Okay, I can assume CPU is here, memory is there, and CPU cannot say I want to read from the memory as well as write into the memory. So this is supposed to be high. Okay, it's not mentioned in the question paper also, you can assume that. That means read is not the operation being done, and write is going low here. That means write operation is supposed to be performed here. Now imagine a CPU is the one which is a master initiating any transaction with the memory. That means it is going to give an address at, and we have understood that it's a write cycle. That means its CPU is trying to perform a write operation onto the memory. So that means it's supposed to give a data. So that is also being given by the CPU. Okay. This, what does it mean? This kind of a block. It means that the signal value what is there from D0 to D7. That means there are 8 signals coming out. Okay, they are shown as a single line. This particular thing represents that it could be a 0 or 1, D or D0, D7. We don't know. Whatever may be the value which is going to be used by the CPU. Is giving out that value. Data is coming out of the CPU and getting written into the memory. Okay. So that's what it means. Okay, let me erase it so that it looks a little cleaner for you to understand it. Now let us use some different color for a change. Now what happens? Okay, it's very difficult to read it, so let me use a dark red only to see where the mouse is. Now what happens? We have a positive edge and memory request is going. That means memory request is, it is CPU is going to ask the memory, I'm going to do some operation with you, so please be ready, by bringing it low. And then it is going to perform either read or write operation. By bringing it write signal low, it means that I'm going to perform a write operation. Now once it is performing a write operation, memory knows that data is available here. By the time it makes this write signal, it make sure that the data is already stabilized and it is available on the data bus. And memory's address is also there in the address bus, which is A0 to A15, that is 16 bit. There is 2 power 16 locations can be accessed, and it's a 8-bit data which is getting written into. Now what happens when this signal is given? Okay, memory request is there and a wait signal could become high to indicate which is coming from the memory. Okay, memory says I am trying to get ready based on your request, so I am rising it up, so please wait. Now during this time, this write signal has gone down and then wait signal also down. That means what? It says that okay, I have understood your write signal and the memory has latched the value that has been given as a data, and then it has latched the address also, so it is going to write into the memory. So once the wait signal is taken out, then CPU will come to know that okay, write operation is done, the memory is taken the data, so it can say that okay, I am going to end my write cycle by bringing the write up as well as memory request up, then it will withdraw the data which is latched by the CPU. Remember, to summarize this discussion, let me explain everything. Initially, CPU is going to put the address, it is going to make the data available on the database, and then it says that I am going to ask for some request from the memory. Memory says wait, then it says I'm interested in you writing it, data which is available here. Then memory looks into the database. Till then it will not know whether to read from the database or not, because there should be a valid data on the bus. And it brings down the wait state saying that okay, I am ready to take the data in, and by bringing it low, it is communicating back to the CPU saying that I have read your data. Now you can safely take the write cycle, you can end the write cycle. So it brings up, that means okay, right, no longer memory request is valid, it has become high now because it's actually low. Once the signal is high, that means CPU is no longer requesting anything from the memory. Write signal is up, that means it's not a write operation or a read operation, both are high, and then the data is withdrawn from the CPU. CPU is no longer driving the data onto the data bus. So that is also taken off. Maybe it's a floating state or something, which is nobody is driving anything on the data bus. And then the address is also changed. Okay, after this clock cycle, third clock cycle, the write cycle is done. So this is the signal flow between the memory and CPU. and this need not be the same. Okay, it can be different for different memory and different CPU interfaces. So I'm going to show you few more signals which you should be able to understand. Now this is another signal. Now same thing, like memory request is coming, and then together it is saying read cycle. Okay, that means what? It is going to ask the memory to put the data out. CPU is not going to put the data because it is reading from the memory. So it says that I want to read from this particular address, but CPU should say which address it is reading from. So address is put by the CPU, but data is going to be put by the memory. Now again, memory will take more time to look into the its content and bring out the specific content of the memory stored at this address, because it has to latch the address, take it in, and look at the content of that particular thing and bring it out to the data bus. So it takes some time. How does the CPU know that it has to wait? So it is going to, CPU memory is going to make it high. Wait signal is an active high signal. So when it is high, CPU will know that memory is busy, it's not ready with the data, so let me not disturb it. So it will wait. The memory cycle, read cycle is still pending. Now once the CPU, no, memory puts the data at this point, it will bring down the wait signal. They're saying that, hey, I have put the data now. Then CPU, as long as it, as soon as it sees that the weight is going down, it means that the data is ready, so it will latch the value in this particular edge. Okay, or it would, it may be even during this time, CPU is supposed to take the value, and then it takes the value, and then it brings up this value, right? Read signal and the memory request signal, and things are back into thing. That means this data which is put by the memory is read by the CPU. So this is a good example of a CPU reading from the memory. Okay, so this actually maybe the right thing is to say that clock is a bar, because negative edges are only is sorry, here negative edge is used for latching the data. Okay, positive to negative. So this may be a right thing. Okay, during the negative cycle things happen. Okay, so don't need to worry about much about this. Here you are not hardware engineers. I want you to just basically understand that CPU and memory, how they talk to each other, and how does the wait signal help in making the CPU wait for the memory to be ready with the data. So this is a good example of a memory read with the from the by the CPU. Now another signal I am showing you here. From this signal you should be able to find out whether it's active low signal or active high signal. These are all active high signal. Memory wait also high, memory read is also high. So it's also very specific to the memory and CPU. So need not be always bar no, or it could be a single signal also. Okay. Here memory read is high means it is performing a read operation. Now who is generating the signal? CPU is generating it. CPU is generating it. Memory address is generated by CPU. Mem wait is generated by the memory, and the data is generated by the memory. So data is coming here, and then after the data is put, it is bringing down the wait signal. Memory is bringing down the wait signal to indicate that I have put the data, you take it. Now CPU knows that, and it takes it during the edge. Okay, or if it is a positive edge, it will latch on to this positive edge here. Data is latched in the positive edge because clock is given as a positive edge clock signal. So it is actually latched here. Okay, sorry, it is actually latched in the positive edge here, and then it is bringing down the memory read cycle because it is data is latched here on the positive edge. Okay, so this is a good example of memory read cycle. Okay, as I mentioned, data is latched here during the positive edge because clock is positive here. And what is this timeline? This timeline shows that it may take varied number of different time. It may go up anywhere here in between, and then there is a break in the clock, means that this can be as long as the memory takes its own sweet time. So it depends on the, this bit depends on the number of clock cycles that may be lost due to the memory being slow. And then when the memory is ready, the actual events are captured. Okay, this is how you have to understand. This is actually part of this section 3.1 in the section. Okay, So this actually brings our discussion on memory read and write cycles. I hope this is clear to you. Now finally about Arduino IDE, which we use normally for writing programs. But instead of Arduino IDE, I am actually showing you a C program, not the Arduino IDE, I'm sorry. What are these variables and where are they located? Okay, so C program, different memory areas are there, and we have a function int variable, static variable, and we need to tell which variables are residing in which location. Okay, so let me show the actual solution rather than me explaining this. So actual solution is int var, which is a global variable, is data segment. Remember, all the static and global variables are in data segment. So yes, main int and int var. S main int is S static. So static is also in the data segment, even though it is within the main, it is a data segment. S int is a static global variable and is outside, which is local to this file. Whereas S main int is visible only within the main, whereas int si var is visible within the file, whereas int var is a global variable which is across the file. Throughout the program it is visible, though the visibility of these three variables are different. They all live during the program execution, so throughout the program execution, because they are all in the data segment, there is not in stack segment. Now what about the uninitialized data? That means if a user is not initializing it, it will be initialized by the program, so by the tool. So s main int is initialized by to 10, s int is somewhere here 200, which is also initialized values. So initialized values are put in the data segment together, and uninitialized global variable and static variables are together, which is also in the data segment, but they are all filled with 0. And then all the local variables are in the stack. So this is what you are supposed to explain. And then what does the program do? It is calling this myIntVar, and it executes and adds them and then puts it. So you can even show the value of what is getting passed and then what gets returned as an output. So you can see that this program is getting intvar, which is initialized to 100, and sivar, which is a 0, which is getting passed, and then k, which is initialized to 1, which is local variable. So 1, these three values are coming in, and then s int is initialized to 200, so 200 is getting added. So finally the result will be 301. So that's all. I think this is very clear. A C program, and various variables, where are they located, and we can actually read some of the sections related to this program and understand it if you want if you have any doubts. Okay, so this brings our discussion on the question paper fully, and I wish you all the best for the exams coming up, and see you later. Bye bye.